Yes. Okay. So it was an interesting trip here. I got to see a lot of Rio on the way over, but we made it. Anyhow, what I want to talk about today is the Kronecker-Weber theorem in function fields. And there is such a thing, and I don't think the formulation of it even is widely known. So I'm going to spend some time just setting it up. And the proofs that, that I know of use class field theory. So a contribution of the talk will be to show a way of getting the main results without using class field theory. But I apologize to those of you who are familiar with this circle of ideas, and because I'm going to explain the situation in some detail in the function field case. And one more thing is that although in number fields, you only have a type of Kronecker-Weber theorem that is an explicit generation of the maximal abelian extension of a number field in two cases, over the rational numbers and over imaginary quadratic number fields. And in no other number field do we have an adequate substitute. Whereas in function fields, as I hope we'll see, there are formulations for an arbitrary global function field, so a function field over a finite field as base. And this is quite a difference between number fields and function fields in our knowledge. So, and one last remark is because it's only an hour, I'm not going to go really into the global function field situation in general, but talk about the rational function field as base because it's easier to deal with. But it gives you some of the ideas that go into the formulation and proof. So to begin with, just a little bit of history. The Kronecker-Weber theorem was proposed by, well, it wasn't called Kronecker-Weber. Kronecker proposed that over Q, every finite abelian extension of Q is contained in a cyclotomic field. Okay, so Kronecker's proof contained an error which was supposedly corrected by Weber in 1886, so that's already quite a while later. But in 1979, Neumann found an error in Weber's correction. So the first proof, which is now generally accepted as valid, was by David Hilbert in 1896.
And is Kronecker's proof not feasible?
I suppose not. You know, I don't know the history in detail, but I mean, I think that's what Weber tried to do. And he gave an alternative proof, but it wasn't good enough. Although it seems to have been good enough to fool people for a long time, because Neumann's found an error in that proof many, many years later. So it gives you an idea of how history goes. Anyhow, in 1900 at the International Congress, Hilbert proposed a famous set of 23 problems. And the 12th problem concerns a generalization of Kronecker-Weber. He said, let K be an algebraic number field, find a function g of z such that every abelian extension of K is obtained by adjoining a value of g of z for the values coming from the base field. This is to generalize the Kronecker theorem, which you use the function e to the 2 pi I z, and you substitute for z rational numbers, and those values generate the maximal abelian extension. So the idea was to find the generalization of that. And Kronecker had proposed a solution to this problem for the case of imaginary quadratic fields. It's so-called the Kronecker-Jungentraum, dream of his youth. But that his proposal turned out to bear fruit because it was established, and we now... The first idea was to use the J function, the famous J function on the upper half plane, as your function. And it almost works, but it falls short. The special values will generate a subfield of the maximal abelian extension, where you can say a lot about the field from there to the top. But the usual formulation is you use two functions, j of z and a Weber function, which is related to torsion point. I mean, the values you get are related to torsion points on the associated elliptic curve. If you have an imaginary quadratic field, the ring of integers form a lattice. And so you look at the complex plane modulo of that lattice and so on. An interesting point there is that the elliptic curve is not defined over the CM field. I mean, if you have q to the square root of d, the smallest field of definition for the elliptic curve that you want to take into account is the Hilbert class field of K. So you can't stay at K in order to do the theory. You have to go to the Hilbert class field. In the general case, which I won't discuss in detail, you have to do a similar thing in function fields. Okay, so many attempts have been made to solve the Hilbert's 12th problem, but a complete solution is still only known for q and q to the square root of d. Okay, so part two, other fields. I mean, you can take any field and ask for an explicit construction of its maximal abelian extension. The easiest field you could do would be a finite field. But we know that every finite field, if you have fq to the n, is generated by a root of unity, because fq to the n star, the multiplicative group, has q to the n minus 1 elements, and it's a cyclic group. So you just join a generator, so a q to the n minus first root of unity will generate any that abelian extension. And if you add all roots of unity, you get the maximal abelian extension. So this is not quite idle. I mean, it's like a toy case. But in the case of local fields, the maximal unramified extension is obtained by adjoining roots of unity, because you first do it for the residue class field and then pull back to the local field. So anyhow, here I'm now going to describe Kronecker-Weber type theorems for function fields, and actually just very sketchily show you what the story is for local fields, where it really comes from Lubin-Tate theory, the famous paper of John Lubin and John Tate. Jonathan Lubin and John Tate. Okay. So other fields. The two other types of fields which make sense to ask a Kronecker-Weber type theorem is possible. If F is a finite field, look at the ring of polynomials, which has been discussed at this conference quite a lot. Call that A, the standard notation for this thing. And it has many properties similar to Z, as you all know, so I won't dwell on that. Well, to just carry out, if F is a polynomial, then the residue class field A mod FA is finite. So this analogy is amazingly precise between polynomials and integers, and it was been noticed early and used throughout the history of number theory. Like Gauss used this analogy. Okay, so let K equal f of t, the rational function field in the variable t over a finite field Q. Okay, and that's just the quotient field of A. Okay, a finite dimensional field extension of K is called a global function field. I mean, there are many ways, if you have an algebraic curve defined over a finite field, the ring of regular functions on it has a quotient field, which is another way of looking at it. Has many properties, global function fields, many properties analogous to algebraic number fields. And in 1974, David Hayes published a beautiful paper entitled Explicit Class Field Theory in Rational Function Fields. It's an interesting story. Leonard Carlitz, who's a well-known number theorist, He published hundreds of papers. And in the 1930s, he published a paper called A Class of Polynomials. That was its title. It really an innocuous title. No one looked at this paper, I guess, because there was no mention of it ever again until David Hayes wrote his thesis. But what it is a construction of abelian extensions of the rational function field, which is not so easy to do because if you just add roots of unity, that's like constant field extensions. And so constant field extensions are abelian extensions, but as is well known, there are many geometric extensions, and these are not taken into account. So adding roots of unity only gets you part of the way to the top. But Carlitz discovered a way of generating abelian extensions remarkably similar to cyclotomic extensions. So it not only produces abelian extensions, but small modifications produces almost all abelian extensions. So these polynomials are just like cyclotomic polynomials, and their roots play the role for f of t that roots of unity play for q. So you can say that the main theorem of David Hayes' paper, is a Kronecker-Weber theorem for f of t. So Carlitz never proved that his construction, which has to be modified, produced all abelian extensions, and that was the main result of Hayes' thesis. Once this has been done, you can ask similar questions for other global function fields, as I've said. And the main tool in doing this, I mean, this has been done, is the theory of Drinfeld modules, which was invented by Vladimir Drinfeld in 1974. Subsequently, David Hayes simplified Drinfeld's work and refined his theorems in several ways. And his paper that appeared a few years later, Explicit Class Field Theory in Global Function Field, also produces a sort of a Kronecker-Weber type theorem in general. But once again, he needs to use class field theory to establish the results. Okay, so I've been interested for some time in getting around the use of class field theory. Not that I don't like class field theory, but it's a big and difficult subject, and it's sort of nice to be able to prove this stuff by more elementary means if you're able to. So, and there's a history of people giving elementary proofs, for example, of the Kronecker-Weber theorem. So it's something that's been done and been of interest to people. Okay, so the way I'm going to do it is to first look at local fields and use Lubin-Tate theory to prove a Kronecker-Weber type theorem for local fields. Okay, and then the idea is to get it for global fields by localizing and using, you know, the principle that if something is true in every localization, then it should be true in the original field, which doesn't always work, but it does seem to work in this case. Okay, so first, the meaning of the local Kronecker-Weber theorem. So that means over I think in our case, we want to look at the local field as the Laurent series over a finite field. In characteristic 0, finite dimensional extensions of QP are local fields. In characteristic P, finite dimensional extensions of F double brackets 1 over T are the things that one looks at. Okay. Okay. Okay, so unfortunately, I noticed last night that I used the letter K for too many different types of fields. But right now, in this section, K is a local field, O is the ring of integers, and P is the maximal ideal. So O is just all elements of absolute value less than or equal to 1, and P is all elements of absolute value less than 1. Okay. Now I want to define a Lubin-Tate polynomial. So a polynomial with coefficients in O is called a Lubin-Tate polynomial well, the maximal ideal is always principal, but pick out a generator, or uniformizing parameter, call it pi, and called F a Lubin-Tate polynomial the first thing just means that the linear term of the polynomial is pi x. The constant term is 0, the linear term is pi x. And the second condition is that if you take your polynomial and reduce the coefficients mod p, the maximal ideal, you get reduced to the polynomial x to the q, which is like the Frobenius substitution in our context. It'll be an endomorphism of certain formal group and serve that function. Anyhow, one doesn't have to go deep into Lubin-Tate theory to get what we mean here. So even though the whole thing is based on the theory of formal groups and always talks about power series, so if you look at the original paper, they say a power series with coefficients in the ring of integers is a Lubin-Tate power series. Of course, these power series don't always converge, but if you look at certain types of power series and restrict yourself to the elements of the algebraic closure of K, which have absolute value less than 1, then they produce the power series that are involved are convergent, and you can do business there. But for my purposes, I don't need the whole construction, the proof. I just need to pull out a polynomial, which is Lubin-Tate in this sense. And then what you do is you simply iterate. You take f of x, or yeah, I think the variable x is the right one here. So f of x, f of f of x, f of f of f of x. And in general, f parentheses n is the n-fold compositum of f with itself. Okay? So that's easy to do. And finally, let lambda pi to the n be the zero set of f n of x in a fixed algebraic closure of K. Okay, so these are, by the way, you know, if you want, the Lubin-Tate polynomial you can use is just pi x plus x to the q. So you don't have to do anything very fancy, and just iterate those things and take their roots. And as simple as that is, here's what happens. So here's a theorem. Let k lambda pi to the n, just add the roots of f composed with itself n times. It's an abelian extension of k and of degree q to the n minus 1 over q minus 1. So another thing I noticed last night when I was reviewing this is that I use q for too many things. Here it's the residue class field of the local field, but later in the talk I'm going to use it as the number of elements in f, in the rational function field f of t. And then we won't have q in the local case, but we'll have powers of q, because we're going to look at the residue class field when you pass to the completion, and that will be bigger. So, but for now, anyhow, there's no confusion yet, so this is correct. The second thing is that k of lambda pi to the n over k is totally ramified. And finally, the Galois group of that field is isomorphic to O mod p to the n star, the multiplicative group in the finite ring O mod p to the n. And here is the local Kronecker-Weber theorem. Here a finite abelian extension. There are integers n and m with p not dividing m. P is the characteristic of k, which is also silly to say. I should have said P is the characteristic of the residue class field of K. Because this theory of Lubin-Tate applies to characteristic 0. In fact, in some sense, that's the most interesting case. So this line should be modified. But anyhow, the upshot is that any abelian extension of K is contained in a field to which you've added the nth roots of unity and the elements of pi to the lambda pi to the n, which is just the zeros of a certain, concrete polynomial. And that's a beautiful theorem, I think. Remark, lambda pi to the n can be made to be an O module. O is the ring of integers in K. And as an O module, it's cyclic. Okay, so if it's cyclic, let lambda pi to the n be a generator as an O module. And then if you just add lambda pi to the end, that's enough to get L contained in that thing. So you just have to add one root, a primitive root, so to speak, and you're there. So it's very similar to cyclotomic theory. Okay, so that's the local situation. And it turns out, I don't know why, but in the decade from 1975 to 1985, roughly, well, 86, a number of people decided to try to prove this theorem, this local Kronecker-Weber theorem, without resorting to class field theory, as Lubin and Tate do in their paper quite strongly, and were successful. So the first one was Hazewinkel, Bob Gold had a paper, Lubin, myself, and a little bit later, Iwasawa. The one, I like my proof very much because it avoids higher ramification groups, which I find to be a virtue. Not everyone does. I use the structure of a Galois group acting on the principal units, which I like much better. However, it doesn't work in characteristic P. For the purposes of this talk, my proof doesn't count, so you have to pick one of the others. So, for example, Lubin's proof is fine. But it uses higher ramification theory quite strongly. Okay, so next, I'll sketch a proof of Kronecker-Weber for the rational function field using the local Kronecker-Weber theorem, which we just decided. So what does this mean? So I have to describe a Kronecker-Weber theorem for the rational function field. And to do so, I have to tell you about this construction of Carlitz, which is very, very clever. So looking backwards, Carlitz never called his construction the Carlitz module, but it's a special case of Drinfeld modules, and so now it's referred to as the Carlitz module. It's the first module of this type constructed. So first, some notation. A is, well, we've done that already. The number of elements in the finite field is Q, which is a power of the characteristic. Omega is an algebraic closure of K. And then if you complete at a prime, you complete K. Kp is the completion of K at P, where P is a monarchy irreducible. And omega P is a fixed algebraic closure of Kp. In most of the sources, actually, when you get to omega P, you take the closure of that, and then you get what's called Cp. It's sort of an analog of the complex numbers if you're at the prime at infinity. But this is enough for my purposes. We're going to make omega, so we're in the global case, it's the algebraic closure of little k into an A module. Of course, it's already an A module. A is in K, and you can just take an element and multiply it by something in A, and that makes it into an A module. But the idea is to deform that action somewhat. And so what you really want to do is you want to map A into the endomorphisms of omega considered simply as an additive group, or maybe as an algebra over the constant field. And there are lots of endomorphisms in characteristic P. In characteristic 0, the only endomorphisms are given by multiplication by elements in A. So you can't do anything like this in characteristic 0. But in characteristic P, we all know raising to the qth power has the pleasant property that u plus v to the q is u to the q plus v to the q. And that says it's an additive endomorphism. The additive structure of omega, is the Frobenius is an endomorphism. And since I'm raising to the q, not to the p power, so the number of elements, and it's an endomorphism as an F algebra. Okay. So what we're going to do is consider a certain ring of endomorphisms, which I call AQ of K. It's a set of polynomials G of U, which are additive. G of U plus V is equal to G of U plus G of V, and preserves the scalar multiplication. G of alpha U is alpha G to the U. So this set forms a ring with the usual addition and the product being composition. So in particular, it's easy to see, it's not a commutative ring. It's a non-commutative ring, but it's still useful. And G of u has these properties if and only if G of u has the form. So all these polynomials in AQ of k are of the form a0 of u plus a1 u to the q plus a1 u to the q squared up to the n. So the ring consists of polynomials of this form, where the a are taken from k. In the case of the Carlitz module, the ai will actually be taken from capital A, the ring of integers in k. Okay. So there's a unique homomorphism from A into this non-commutative ring. You just have to tell me where T goes, and that automatically extends to an endomorphism of the whole thing, because polynomials are freely generated as an algebra by T. You tell me where T goes, and the rest follows. So what Carlitz chose for his what the endomorphism corresponding to T is, C of T of u should be Tu plus u to the q. Okay? So that's an additive polynomial which commutes with scalars and so on. So it does everything we want. And now let's just calculate C of t squared. That's C of t composed with C of t. And you just, work it out, and in a few moments, you wind up with this formula. C of t squared is t squared u plus the coefficient t plus t to the q times u to the q plus u to the q squared. And you can go to t cubed, and so on. So you see the pattern, and then take linear combinations. And the general result is that Cm of u is a coefficient, which I'll call m, brackets m comma 0. Second coefficient is m brackets 1 all the way to the top. And the degree of the polynomial C of m is q to the d, where d is the degree of m. Like here, q squared is quadratic polynomial. Okay, and you can prove that the intermediate terms are polynomials in T, and their degree is d minus I to the q to the I. The constant term, the coefficient of u, is just m. And the leading term, which I haven't written here, but the leading term is just the leading coefficient of m. So m over 0. So in particular, if you take a monic polynomial, this polynomial will also be monic. Okay? All right, and now you make omega, the algebraic closure of K, into an A module by defining m times omega, little omega, to be C of m evaluated at omega. Because of the fact that we have a homomorphism into this ring of endomorphisms, this is a module action that's easily checked. So it's a new way of making the algebraic closure into a module. Omega with this structure is called the Carlitz module. That's not a usual definition, but for this talk, I want to fix the set that I'm talking about, and it's the algebraic closure of K. Okay, this is due to the Carlitz, and there's his famous paper, now famous, A Class of Polynomials, 1938, which, embarrassingly, I'm getting so old, is the year that I was born. But I didn't know about this paper at the time. All right, so now let's take a polynomial in A, m. Let's say it's monic. It's not that important, but let's say it's monic for definiteness. And then define lambda m to be the set of all omega in capital Omega such that m omega is 0. So m omega will be a certain polynomial in U of degree q to the d. So the roots here will have q to the d roots. And it's a separable polynomial, so they'll all be distinct. And here's the theorem. As a module, so lambda m, remember the whole omega is an A module, so this set of torsion points is mapped into itself, easily seen by A. It's an A module, and it's a cyclic A module isomorphic to A mod MA. The extension that you get by adjoining lambda m is an abelian extension, and the Galois group of that extension is A mod MA star. And something that I didn't write down, but is important, the only primes that ramify in this extension are the primes dividing M. And actually, there's one more prime that ramifies. The prime at infinity ramifies in this extension. So, so that's if you're not in that set, it's an unramified extension. You know, if Q is a polynomial in A, and you look at you know, the ramification of Q in the extension K of lambda M. Yeah. Okay. So the question is K of AB, is the maximal abelian extension equal to the union of these fields? And the answer is no, because constant field extensions are also abelian extensions, and all these extensions, I neglected to say, have no constant field extension in them. So we missed the whole bunch. This is not quite the whole answer, but you would think, suppose you just throw in all the constant field extensions, pull that K bar, so a K bar would be the maximal constant field extension. Okay, is then the maximal abelian extension equal to K bar times K of lambda? The answer is no, because all these fields are ramified at infinity, but they're tamely ramified at infinity, and in fact, the ramification index is Q minus 1. So, and there are, you can easily show, wildly ramified extensions at infinity, so we're still missing things. So how do we take care of that? Well, you go to infinity, and you do a simple trick. You take the Carlitz module construction, but you don't apply it to f of t, but apply it to the polynomial ring f of 1 over t. 1 over t is a parameter at infinity. So f of 1 over t, which I call A prime, is a polynomial ring in 1 over t. 1 over t is still transcendental. You can repeat the construction where you send 1 over t to 1 over tu plus u to the q, and so on, and generate abelian extensions by the same business, iterating this n times, and you get a polynomial in 1 over t, and you join roots of that, and what I call this is lambda of infinity to the n. So this is an explicit thing gotten by roots of a certain explicit polynomial. So this can be thought of as a cyclotomic type polynomial. And this thing has the same properties. For example, the degree of this extension is q to the n minus 1 times q minus 1. Something here says not quite correct. I said these are totally ramified at infinity and nowhere else. Wrong. They're totally ramified at infinity, right, but the prime at 0 ramifies in these things. There's kind of a reciprocity. So these things are ramified at 0, also with ramification degree q minus 1. So they're a little ramified at 0. Okay, so now, are we finally through? Yes. So here's the theorem phrased in an elementary way. Take the rational function field and an abelian extension. There is a monic polynomial m and two integers little m and little n, such that k is contained in the compositum of the fields k of lambda m, you know, the Carlitz field, k of zeta m, which is a constant field extension, and k of lambda infinity m, which are sort of torsion points in infinity. You take these three fields, put them together, and every abelian extension is contained in that. So by adding torsion points on various natural objects, you get what you're after. This is the full statement. Okay. So, all right. So it's quite beautiful. I think you see it's a nice generalization of classical Kronecker Weber. So how do you prove it? And as I say in Hayes's paper, it uses class field theory, so I'm going to now sketch. I don't have time to do the whole thing, but I'm going to sketch a proof of this theorem, assuming the local Kronecker-Weber theorem, which we have seen a number of papers showed that that can be done without class field theory. So it's fair game to use that. Okay, so here's how that goes. We're leaving details out of it. Our goal is to prove Kronecker-Weber for f of t without using class field theory. The idea is to reduce to the case of a local field. I've said this. Okay, so let p be a monic polynomial of a, and let's look at c of p. The leading term is pu. This is just using the definition of the Carlitz module, and the other, the maximal term is u to the q to the d, where d is the degree of p. Carlitz shows that this is an Eisenstein polynomial. So one of the things he proves is that all the intermediate coefficients are divisible by p. So it's an Eisenstein polynomial, which tells you that if you add the roots, for example, you're going to get a totally ramified extension, right? If you add the roots of a Eisenstein polynomial, you get totally ramified. So to make things a little easy notational, let's call Cp of u Fp of u. One sees that the linear term is pu, and if you reduce mod p, assuming Carlitz's result that this is an Eisenstein polynomial, you'll get Fp of u is u to the q to the d mod p. Now remember, if you go to the localization and you look at the ring of integers there, O mod p, the number of elements there is q to the d. So in the local ring, this Carlitz polynomial is a Lubin-Tate polynomial. This is the key observation, that the Carlitz polynomial, when you localize, is a Lubin-Tate polynomial, and I can apply Lubin-Tate theory. So not to go by that too fast, that's a key thing in my proof. So thus, Fp of u considered as a polynomial over OP, the local ring of integers, is a Lubin-Tate polynomial. Okay. So now let k over little k be an abelian extension. By the local Kronecker-Weber theorem, there exists integers n and m with p not dividing m. That's the unramified stuff. And define kp to be the compositum of the localization of k of p with some embedding of k into the omega p, the local algebraic closure. It's not hard to see that you have it's sort of rigid. You take one embedding, and all the other embeddings are obtained by just applying elements of the Galois group of k first, and then following up by the embedding. So it's fairly unambiguous when you think about it that k will sit in omega p. So in that sense, this is a finite dimensional extension of kp, and it's abelian. So it's finite dimensional and abelian, and so by the local theorem, it's contained in kp after you've added an mth root of unity and a p to the n torsion point. Okay. Now, what's interesting about this is that in here, it's a constant field extension, and then you add lambda p to the n. So you can compute what the ramification is. It's all at the top, and it's the degree. I mean, the ramification degree is the degree of lambda p to the n, which is phi of p to the n, where phi is the generalization of the Euler phi function. It's the norm of p to the n times the product 1 minus 1 over the norm of p for primes dividing m. So that's the ramification of this field, and so k, which is sitting in there, its ramification is dominated by that. Okay, so now what you do is let p1, p2 up to pt be the primes of A which ramify in K. K is the global field. You look, there are only finitely many primes that ramify there. And let Ni and Mi be the corresponding integers. You get each of these, we'll get put an index I here, and then for zeta sub mi, p to the ni, and so on. So if infinity ramifies in k, let n infinity and m infinity be defined in the same way using the modified Carlitz module. All right. So then we have, you take capital M to be the product, as you see, and let M equal the product of the mi and m infinity, if m infinity is there. If infinity is ramified, you also want mi to be defined in that way. And what you get is a theorem. K, so it's a little bit more precise than the Kronecker-Weber theorem as I stated it. Its K is contained in the compositum of this root of unity, K of zeta of m, adding the capital M torsion points to, and taking what they generate over K, and taking the torsion points at infinity and throwing those in. If you put in those three things, you get the Kronecker-Weber theorem for the rational function field, and with, as you'll see, no use of class field theory. Okay. So, all right, so how does one do that? Well, it takes a little while to give the details. But before I do that, let me check on the time. So when did I start?
Yep, till 10. 10 after.
10 after, yeah. Okay. Okay, so before I give a sketch of the proof, let me just say a few words about the general case, which I'm not treating. So what happens in the general case if your base field is k, you know, a general function field, then the question is, if you have a general function field, what is the analog of the Carlitz module? You want to find a Drinfeld module that behaves like the Carlitz module. And just like in the imaginary quadratic field case, you can't find one defined over K. It just doesn't exist. However, if you go up to the Hilbert class field of K, I got to explain what that is. And then you take a small extension of that. I don't want to write plus, I'll write prime. So in the function field case, so A contained in K, what is A, for example? So you're a general function field. What you do is you choose a prime at infinity. Any prime at all, you single it out and call it the prime at infinity. Because the Carlitz construction and Drinfeld module construction is really kind of an affine construction. So you don't do it for everything at once. So you find such a prime in here, and then this A is the set of elements in K whose only poles are at infinity. Okay, so if you look at functions whose only poles are at infinity, A, you can prove, is a Dedekind domain. So that's nice. And this A will serve the role. And HK, the Hilbert class field, is not the maximal unramified extension of K, maximal unramified abelian extension, because that definition, the Hilbert class field, is always infinite because it contains all the constant field extensions. So the definition of the Hilbert class field theory in this theory is it's a field which is unramified at all finite primes, and at infinity, the prime at infinity splits completely. So it's unramified at infinity too, but you add the extra condition that the prime at infinity is split. And then HK over K is an abelian extension which is finite, and the Galois group turns out to be isomorphic to the class group of A, considered as a Dedekind domain. So it's not the divisor class group, but it's the ideal class group of A. So it's a nice representative of what we want. However, the modules that David Hayes defines, which he calls sign-normalized Drinfeld modules, are defined over hk prime, which is called the normalizing field. And he writes down these modules. And then the whole theory goes as before. The torsion points on those modules give you nice abelian extensions of this field, whose Galois group we can compute. And the nice thing is that those torsion points are actually, when you add them, you get abelian extensions not only of hk prime, but abelian extensions of k. So you get something that looks like a Ray class field. Okay. So I just wanted to say that much about the general theory. And this thing works out, but to explain the details would take a long, long time, so I decided to stick to the rational function field. Okay. So now, just to finish what I'm saying, let me quickly just sketch the proof. You don't worry about the details. Define a new field L. Remember, I've defined M and N by looking at primes and looking at the embedding locally in the local fields and using local Kronecker-Weber. So L is going to be the compositum of k. That's the extension of little k. K is the abelian extension of little k that we're talking about, composed with k of lambda n and k of lambda prime at infinity. And just a technical assumption, the proof I'm going to give you doesn't quite work if t divides m, so let's assume it doesn't. I have to modify the proof if t divides m. Okay. Let H be the product of the ramification groups of P1, P2 up to Pt and infinity. So each of these primes is ramified. They have ramification groups in here. Take the product of the ramification groups and take that's H. The fixed field of H is everywhere unramified extension of K. And since K is the rational function field, Riemann-Hurwitz tells you very shortly the only possibility for the fixed field of K is a constant field extension. So the fixed field of H is a constant field extension. We'll call that E. And, all right, I already said that. From the local Kronecker-Weber theorem, we can deduce an upper bound on the order of H. It's less than phi of m, phi of infinity to the m. So this thing is q to the n minus 1 times q minus 1, if you don't remember the definitions of that. Phi of m is just the number of elements in A mod m star. You look at the finite ring A mod ma, and then take the units in that finite ring. The order of that is phi of m, just like the usual definition, right? Okay, so we're closing in on the end. So this implies, if you translate what I said, I'm missing a step here. I first look at the index of L over E, because that's an upper bound given by the product, the order of the ramification group, and that was bounded. But now if you just multiply by the dimension of E over K, you get L over K is less than the constant field extension, the degree of the constant field extension, times phi of m times phi of infinity m. So that looks hopeful. Next, consider the index L over K, the left-hand side, and come down in 3 steps. First, L over this compositum, the one you're interested in. And then that compositum, this is with E over here, over E, and then finally to E over K. So just the Tower theorem. Okay. Now, the middle term, I could compute its order if I knew that the middle term was actually equal. The index is the same as the index k lambda m, k lambda infinity prime over k, because that I know is phi of m times phi of infinity to the m. So you have to show that E is disjoint from that other compositum. So that takes a little fooling around, but it's true. So E is, you take 2 fields, E and this compositum. E intersect that compositum is the base field. So the dimension is the same if you pass from E to K. And so we have this middle term. Okay, so from A, B, and C, we find, you see, if you substitute it in, E over K is on both sides. That drops out. And yes, this phi of m, phi infinity to m, that's this thing, that drops out. So if you divide out by common terms on both sides, you get that I'm able to cancel each of these things. So I get that the dimension of L over this compositum is 1. Wow. That implies very easily that E is equal to that compositum. But that's exactly what we want, because remember how L was defined. L was K compositum with the other two things. K is part of L. So if L is equal to this, K is contained in L. So the result says that K, the abelian extension of little k, is contained in the compositum of constant field extension plus two fields were obtained by adding torsion points. This is exactly the result. So, okay, once again, I just want to make a final comment that the thing that makes the whole process work is that the Carlitz polynomial, when looked at carefully, is a Lubin-Tate polynomial in the completion, and that enables us to compare the global and local situation in this case. So, okay, I guess that's it.